Okay, welcome everybody, and thank you so much, Steve, for coming and talking to us today. It is my great pleasure to introduce Stephen Ellner, who's going to give the next IITE seminar talk with the title, I believe, of An Invitation to Spatial Coexistence Theory. So with that, I will give the floor to you, Steve.
Okay.
Thank you very much.
Let's see. Am I sharing now?
Yes, you are.
I'm sharing screen now. Okay. Very good. Thank you all for coming. Thank you to the organizers of this series for inviting me, and really thank you to the organizers of this series for organizing this series. This is really something amazing. You know, we're an international community, but this has brought us together like never before. And it's just such a fantastic opportunity for students. I'm really grateful to the organizers for making this happen. So today's talk is the work of 4 people who you see here. I'm the mouthpiece, but it is a collaborative effort amongst us. You may be wondering why I called it an invitation to spatial coexistence theory rather than an introduction. The reason is that the theory we need mostly doesn't exist. And the main thing I want to do in this talk is to expose what we don't know, motivate why it would be a good thing to know some more, and maybe tempt some of you to work on this, because I think there's a lot of work that needs to be done. So you may be saying to yourself, if you know something about coexistence theory, but wait, spatial coexistence theory really does exist. So for example, what about this paper? A general theory of competitive coexistence in spatially varying environments, where a general model is for a spatially variable environment is developed and analyzed to extend findings on coexistence in a temporally variable environment. So we have spatial coexistence theory, right? Well, yes and no. Okay. Existing theory, including that paper and subsequent work, is about this picture. So the little green dots here represent a rare invader or a species that's down on its luck. And the existing theory assumes that a rare invader is rare everywhere. If it looks around, it sees either empty space or other species, not other members of its own species. So the initial increase of such a rare invader is exponential. But what if movement is limited, dispersal is limited? A rare invader is going to be clustered. It may be globally rare in the habitat, but locally it's common. It's clumped. An invader sees a world that has other invaders in it. There are 2 issues here. One of them is that there's clumping in space, and the other is that we have discrete individuals, and both of those create problems. So let's talk first about clumping in space with continuous population density, not discrete individuals. So one kind of model for that is an integral difference equation model. Reaction diffusion models are essentially the same in continuous time. In one-dimensional space, it goes like this. F here represents local births and deaths. N is the number of individuals at location Y at time t. So we have local births and deaths, and then we have movement, and that tells us where everybody is the next year. And I've put a little subscript t's here to indicate that things can vary randomly over time. So what does this model do? Well, thanks to Newbert, Cotton, Lewis, we know that if you start with a localized invader, a clump of an invader, it grows as a traveling wave with some asymptotic speed. We have a formula for the speed. It doesn't matter what it is. So in 2 dimensions, which is the case we mostly care about, you get an expanding disk that says that the square root of population size, which is basically the radius of the disk, is growing linearly in time. Whereas in the rare everywhere scenario, you get exponential increase. The log of population size is growing linearly in time. So just clumping messes things up from the rare everywhere scenario. And discrete individuals also messes things up. Okay, so Sebastian Schreiber talked about coexistence theory based on invader growth rates. And those assume an infinitesimally rare invader. That is, an invader that stays rare long enough to reach its stable spatial structure. And rare means that the dynamics are described by linearizing the model at zero population density. So as an analog for that, think about a density-dependent matrix population model. So this is a vector, right? N of t plus 1, H structure, stage structure, whatever. We have a density-dependent matrix multiplying the current population. So to see if this population can invade when rare, we linearize the model at zero. And now we have a matrix population model with zero density in A. So this is a plain old Caswell style matrix population model. It's linear. We look at the dominant eigenvalue of A to see if the population goes up or down. Okay, but that dominant eigenvalue describes the population growth when N has reached its stable age or stage structure. Okay, so it has to stay rare long enough to reach that stable structure. And with discrete individuals, right, that doesn't happen. It's never infinitesimally rare. Okay, in a long time, it's not going to stay so rare that we can use the linearized model. So we want to deal with those. Our goal is to come up with a modern coexistence theory that can cope with both of these issues. So let me backtrack. What's modern coexistence theory? Okay, so this is Chesson's approach to coexistence theory that provides ways to quantify the relative importance of different mechanisms contributing to coexistence. So importance is there because it's not enough to say that a mechanism is happening. We also need to know that it makes a difference, and we want to know how much of a difference it makes. Right? This is the perpetual argument, for example, about Jansen-Connell mechanism in forests, tropical forests. Everyone who looks for it sees that it's there. But the counter argument is that it's a very weak force, and if we got rid of it, nothing would change. So it's not really important. So we want to quantify the importance of different mechanisms, not just their occurrence. So modern coexistence theory does this in two steps. We do invasion analysis. We say that coexistence will occur when each species can increase when rare. So its invasion growth rate, E of R, is bigger than zero. We've heard already from Sebastian Schreiber and Nadav Shnerb that this is an oversimplification. There are problems with allele effects and other things in multi-species communities. There are issues with demographic stochasticity. Nonetheless, increase when rare is a necessary condition for a species to persist. So we should start understanding persistence by asking when this is positive. And the second thing is partitioning. We decompose these invasion growth rates into contributions from different coexistence mechanisms or different processes and compare their numerical values. So different mechanisms can be things like storage effect, fitness growth covariance, if you're in the business. Different processes can be rainfall variation, plant soil feedback, whatever. We break things up into pieces corresponding to the components of interest. I'm going to give you an example to set up what we're doing in space, and that's the classic Chesson-Warner lottery model. So we imagine a habitat with n sites and one adult in each site. Every adult of species J produces beta J larvae in year T. Okay, remember beta. Beta is going to be with us for a long time in this talk. Beta is for birth rate per capita fecundity. Then some adults die with the mortality rate delta. Remember delta. Delta is going to be with us for a long time in this talk. If the adult dies and all of the larvae undergo a random lottery, one of them is chosen at random to be the new adult. Okay, so it's competition for space with temporally variable fecundity. With two species, we can write it in terms of just one of them because the total number of sites is constant. It says the population at time t plus 1 is the survivors, the ones who don't die, plus the number of new recruits, which is the number of open sites times the chance of winning a site. This is the fraction of species 1 larvae at each site. And there's no demographic stochasticity. This is an infinite population model and is real valued. So how do we look at coexistence mechanisms in this? Well, invasion analysis says to see if species 1 persists, we linearize around zero abundance for that species. And this is what we get. This is the linearized model. So it's invasion growth rate, it's average little r. This is lambda, so r is log lambda, right? Its average little r is the expected logarithm of this expression. And species 1 persists, we say, with caveats when this is positive. So there's invasion analysis. The second step is partitioning. We express it as this number as a sum of contributions from different coexistence mechanisms. This can be done in a lot of different ways. If you want to see some of the options, look at our 2019 Ecology Letters paper. I'm going to concentrate today on Chesson Classic, which is you break it down into fluctuation, independent mechanisms, storage effect, and relative nonlinearity of competition, which I will now explain. Okay, so partitioning can be done in a variety of different ways. Okay, I'm one slide ahead of myself. So let me explain storage effect. Storage effect is coexistence resulting from covariance between environment and competition. Environment here is the potential for increase under current conditions. So it's a measure of how good the environment is. It's not rainfall, it's how much you like the current rainfall and how much you could increase if competitors were absent. Competition is how much things really are worse because there are competitors. So we write the lottery model this way. Population next year is the population this year times this. These are the survivors, the ones who don't die, and these are the new recruits. E is our environment measure, the per capita larva production. In the absence of competition, every larva would become a new recruit. But there is competition, so they don't all become new recruits. We have to take the number of larvae and multiply by the chance that they actually become an adult, which is given by this, the total number of larvae divided by the total number of open sites. And so storage effect is the contribution to the invader growth rate of the fact that E and C are correlated, okay? It affects things because if there's a positive correlation, then when there's a good year, you also have high competition and you can't exploit a good year. So that's how correlation between E and C affects your potential for increase when rare. Strong positive correlation means that if a year is good in terms of rainfall, it's bad in terms of competition, so you can't take advantage of it. So now we have to partition this into different, partition E of R into different contributions, including storage effect. Classical modern coexistence theory uses quadratic approximations. It makes small variance assumptions, and there are lots of calculations to it. We do something different. We have a statistical hammer called Efenova. Efenova is functional analysis of variance. If you want the full details, you can look at these papers. I'm going to run through how it works for the lottery model. I will point out that one important difference between Efenova and Thor's hammer is that anybody who wants to can pick up Efenova and use it. You don't need to be worthy. Okay, so moving on. How does it work for the lottery model? So here's the little r, and we want to decompose its expectation into a sum of contributions from different things. that have to do with variance in E and C. The no variance baseline is what you get when E and C are not variable. You replace them by their averages. So there's no expectation. The main effect of variance in environment is this, epsilon E. We look at what R would be on average if E varies, but C is held at its average. And the main effect is how much that changes things relative to the baseline. Same thing for C. E is held at its mean, C varies, and we see how much that changes things. Then we have an interaction. We let both of them vary. And I use this sharp notation here to indicate that E is varying and C is varying according to their marginal distributions, but they're uncorrelated. We do random draws from their marginal distributions. And then the correlation is added in, bringing back us to E of R as the difference between what happens when they vary in a correlated manner versus what happens when they vary in an uncorrelated manner. Okay. That's it. This is automatic. You're doing all of this by simulation using either data or E and C values from a long model run, and it gets you the decomposition. We're not quite done. We have to do something called invader-resident comparison, especially for storage effect, because storage effect doesn't really help an invader directly. It helps them indirectly by limiting the growth of common species in good years. The principle here is that the enemy of your enemy is your friend. You only see some mechanisms that act by hurting your competitors if you do a growth rate comparison between an invader species and the established resident species. So in the case of two species, we do this decomposition for the resident invader, decomposition for the resident, exactly the same way, and then we do term by term differences. So that partitions the growth rate advantage of the invader over the resident. And we're going to call those things capital deltas. So here's our decomposition. Baseline, environment, main effective environment variance, main effective competitive variance, the interaction term, and storage effect, the correlation term. Chesson's decomposition is a little different. He lumps these two terms together. We prefer to keep them separate because we think they're both informative. And it omits the interaction term because that's higher order. It's not quadratic. Again, it's a side issue for this talk, but that interaction term can be numerically dominant, right? If fluctuations are important for coexistence, they have to be big. And so when they're big, in fact, the interaction terms can be the largest one. And we talk about some examples of that. Okay, so questions about this. This is basically all of modern coexistence theory on one foot. Invader-resident comparison is really key. This is the stroke of genius in the whole thing, that you can really see all of the mechanisms only by doing a comparison of decompositions between different species, and that's what makes it possible for this to work. Questions about this before I move on?
If you have any questions, just let us know.
Any questions in the chat, or just unmute yourself and ask. Okay, so I'll continue. Let's go back to the real problem. Clustered invaders. We're going to talk about this in a spatial lottery model. We have an M by M lattice of sites with one adult at each site. Each species J adult produces beta J larvae in year T. Optionally, you can add competition between adults. I'm not going to talk about that now. Larvae then disperse according to an exponential kernel with a finite range cutoff. So they can't go to the whole lattice, they can only go nearby. And we use this as the cutoff. It's where the dispersal kernel reaches roughly 0.05. And there's this parameter alpha that determines how quickly it decreases. As in the lottery model, adults die with some probability, and a new occupant is chosen by a fair lottery. So this is just like the lottery model, except that the distribution of larvae at sites is non-uniform because the distribution of adults is non-uniform in space. We assume that the larval population is infinite. There's no demographic stochasticity there, but adult death is a coin toss, and the lottery at the sites are a coin toss. So there are discrete individuals in demographic stochasticity. The first question is, what should we partition? What number, like E of R or C star, tells us if the invader population is growing or shrinking? What do we partition? Well, there's an answer out in the literature. It has to do with this thing called nucleation, which I think first entered the ecological literature in this paper. The idea of nucleation, which comes from statistical physics, is that when a rare species is clustered, clusters will shrink if they're small, but grow if they're large enough. Okay, so this is a geometric effect. It's driven by curvature of the invader cluster. So this is an invader cluster that's big, and this is an invader cluster that's small. And here's an invader at the margin of the cluster. This invader sees a world where other invaders are fairly rare in its neighborhood. Let's say this is its competition neighborhood. It sees mostly resident species or empty space. This invader at the margin of a big cluster sees a world that's 50% residents, 50% invaders and 50% resident species or empty space. So that curvature changes what your local neighborhood looks like if you're at the expanding edge of the population. It's a deterministic thing. It's not an effect of demographic stochasticity, making small patches shrink. It's driven by the geometry. And this idea has continued to spread, so to speak. Cornish and Carrico, 2005, nucleation. Usinowitz, 2005, nucleation. That's what we were expecting to see, and we did not. We saw nothing of nucleation. Let me explain to you what's going on. Here's what clusters look like. This is small clusters in our model where there's fluctuation-dependent coexistence. The invader has a 10% fitness disadvantage, but persists by storage effect. Each number is an invader, and 0 means it has no other invaders as a neighbor. 1 means it has one other invader as a neighbor. 5 means that 5 of its neighbors are invaders. So we do see that they are in fact clumped. A lot of individuals see other invaders near them, and that's going to be important for their lives. So how do clusters grow? To characterize them, we did this. We do many parallel simulations of the models up to some big time t. We use something called the Fleming-Villot method that we learned from Sebastian Schreiber to sample from the quasi-stationary distribution when the total number of invaders is within some range. And these are going to be small clusters. Okay, why quasi-stationary? Well, the long-term fate is that one species or another goes extinct, right? If we wait a long time on a finite lattice. So we have to look at the quasi-stationary distribution where everybody's sticking around. We select lattice configurations where the invader is below some threshold, and then we do many replicate one step ahead simulations to time t+1. Okay, let me back up, right? We are trying to ask ourselves what number tells us if the invader population is growing or shrinking. So we see if we can find one. We look one step ahead, and look at the population change. If the population is growing linearly, the change in n should be roughly constant for different clusters that are small. If it's growing as an expanding disk, the change in square root n should be roughly constant across clusters that are of different sizes but small. And if it's growing exponentially, then the change in log n should be approximately constant. This is what we're hoping for. There's no guarantee that we'll see this. But if we see something like this, it will say that we have some number characterizing the change in population size that applies to all small clusters. And that can be our measure of whether the population is increasing or not. Right? If it's positive, the population's going up. If it's negative, the population's going down. So is that what we see? So here's some simulation results. These are population trajectories, just to show you that the populations are bouncing around but persisting. Here's a plot where the x-axis is initial cluster size, fairly small clusters. This is a small fraction of the lattice, right? This is on a 60 by 60 lattice, so there are 3,600 sites. 100 invaders is still very rare. And this is the average change in population size in one time step. And we see it's not constant. It depends on cluster size. So there's no one number here that characterizes population growth. For square root n, it's the same thing. It changes. There's no one number that characterizes the growth of any cluster in this size range. Peter, Robin, and Giles got sick and tired eventually of me explaining why it was going to be true that the average change in square root n was going to be independent of cluster size. Okay, unfortunately, the real world disagreed with me. And it turns out that the average change in square root n does not at all look constant with respect to cluster size. What looks constant is the change in log n, which says they're growing exponentially, and that makes no sense. But that's what we see pretty much all the time. Now, this line has some slope to it, but that's because we've changed the scale here. If I took this line and put it on this graph or that graph, it would look completely flat. We've basically got one number that characterizes exponential growth in small clusters. Now, there are exceptions to this, and I'm going to show you those in a moment. But it looks like they're growing exponentially. So here I've changed parameters so that you get more small clusters. The invader spends more time at low density. This doesn't work. This doesn't work. This one, now at low density, the average change in log n, E of R, actually goes negative. But this is not nucleation. It's demographic stochasticity. This plot shows us that small clusters are still growing, right? The average increase in population size is positive. What's going on here is that demographic stochasticity creates noise. And when you filter that through the log function, you get Jensen's inequality acting and you get negative numbers. Okay, so that's a problem. Another problem is this. I've been showing you results for successful invaders. What if invasion fails? In this slide, there's a lot of noise and the invaders persist by storage effect. So things look good. This is pretty flat. Again, because the scale is very small, you do see some slope, but it looks like we have roughly exponential growth. If I tune down the variance, it still looks good. But when we get to a situation where the invader mostly fails, we have a problem. Okay, we want negative numbers, but this one is flat. That's odd. This one is flat, and this one is most decidedly not flat. So it looks like there may be different measures of population change that apply to an expanding population and a shrinking population. Okay, now Everyone on board? Let's see if we've been paying attention. Here we've got initial cluster size. Here's the average change in population. Here's the average change in square root population. Here's the average change, expected change in one time step of the log of population. So here's my question for everyone. I've been showing you a bunch of simulation results down here. Why is it that all of them are wrong? What is the actual expected value of the change in log n? Somebody please tell me.
Minus infinity?
Minus infinity. Who is it who spoke up?
It was me, Sebastian.
I can't see. What, Sebastian? Okay, good, Sebastian. Thank you. Yes, the answer is minus infinity. Okay, and that's because there is a tiny, tiny, tiny chance that every single invader adult dies and that every single lottery goes against the invader. And then you get log of 0, which is negative infinity. Okay, so all of these results where expected log growth rate actually characterizes population growth are some kind of conditional mean where that strange event doesn't happen. Okay, so we're on shaky ground. Nonetheless, we're going to persist and show you what we can do if we use this as a measure of population growth. So here are our questions. What does local dispersal and clustering do to coexistence mechanisms like storage effect? How does demographic stochasticity play into this? And how does clustering affect demographic stochasticity? We now have a 3-component decomposition, E, C, and environmental stochasticity. So we do it like this. We say the population size at time t+1 can be written as its expectation given the lattice and environment at time t. There's a formula for this, which you don't really want to see, but there is a formula for this expectation, multiplied by the effective demographic stochasticity. Okay, this is the definition of demographic stochasticity. We do a simulation, we know what happens, we know the expected outcome, and demographic stochasticity is the difference between the expectation and what actually happened. And then we define environment and competition exactly the same way we do in the lottery model. That is, we write it like this. E is again per capita fecundity, and C is whatever it takes to make this equation right. It's basically how much population growth is reduced because there's competition relative to what it could have been. And again, I'm just going to, time is tight. Basically what goes on is we do one step ahead, simulations like we did before, and we do our decomposition by computing counterfactual population changes with and without variation in E, with and without variation in C, with and without demographic stochasticity, to see how those contribute to invader growth rate. And we then repeat this for different values of that larval dispersal parameter alpha to look at the effects of clustering. So here are the partitions for invader and resident. Baseline, main effect of environment variation, main effect of competitive variation, main effect of environmental stochasticity, and then all of the interaction terms. The only one that matters is this one, which is storage effect. The invader is in colors, the resident is in grayscale, and darker colors are more dispersal, more local dispersal, shorter range dispersal. So what do we see? Invader clustering has no effect on the resident. Good. This is a sanity check. If invader clustering had an effect on the resident, it would mean our code was wrong. Okay, so when things get more clustered, variation in C, the fact that competitive strength varies over time, helps the invader less and less. And demographic stochasticity changes. It hurts the invader less and less. And there's also a big effect of co-VC. It gets larger and more negative. So it's hurting the invader more and more as we add more local dispersal. Okay, so these are the separate decompositions, the epsilons. Let's look at the deltas. These are the coexistence mechanisms. This is the no fluctuations baseline. This is relative nonlinearity in competition. These guys are unimportant, and this is storage effect. So there are three things going on. There's the baseline with no fluctuations, relative nonlinearity, storage effect, and environmental and demographic stochasticity. Clustering takes relative nonlinearity and makes it go from trivial to very large for the invader. So that's not good. And it takes the storage effect and makes it get weaker for the invader. Demographic stochasticity hurts the invader in the non-spatial case, but it hurts them less when we have clustering. Okay, so clustering is having multiple effects here. Okay, so what is going on in that demographic stochasticity term? This is the new one, right? Demographic stochasticity adds more variance to lambda, to nt plus 1 over nt. Okay, E of r is the expected log of lambda. So more variance in lambda filtered through Jensen effects, Jensen inequality, decreases E of r. Okay, so to put it another way, this thing, all of this negative contribution of demographic stochasticity is variance filtered through the log function, giving a negative contribution to the expected value of log lambda. And clustering changes that. Why does clustering change that? Clustering changes that by decreasing the variance at the lottery stage. If invaders are clustered, then most vacant sites are in one of two situations. Either most of their neighbors are invaders because invaders are near each other, or most of their neighbors are residents. Either way, the lottery is less uncertain. Okay, right? Binomial. The variance is highest at p equals 0.5. If p is close to 0 or p is close to 1 in a coin toss, then everything's predictable and there's low variance. So clustering makes the lottery outcomes more predictable. And this is not just me talking. This is also Robin doing simulations to show that this is what actually happens. Okay, so the x-axis here is a measure of clustering. It's the number of neighbors, if you're an invader, that are also an invader species. So that measures clustering. And the y-axis is the variation in lambda, given the lattice site, the lattice configuration. And as you can see, when there's more clustering, the variance in lambda goes down. Okay, so more clustering gives lower variance in lambda because there's less demographic stochasticity at the lottery stage, and therefore we get an increase in log lambda. Okay, so there we are. In conclusion, we know how to partition, but we're not sure what to partition. I did E of R. We know that it's not perfect. But interesting things seem to have come out of it. So it would be nice if we could put a little bit more certainty on what we want to partition. There is the possibility that there's no single what. The way population grows for a successful invader may be different from the way it declines when an invasion fails. And this is not entirely unexpected. In an integral difference equation, a successful invader increases quadratically. An unsuccessful invader decreases exponentially. Okay, so increase and decrease are characterized by different rates, different, yeah, they happen in different ways. Nonetheless, if we persist and use E of R as our persistence measure, we see that local dispersal and clustering has multiple effects on coexistence. It weakens fluctuation-dependent coexistence in two distinct ways. Storage effect gets weaker. Jacob Usinowitz already saw this in his 2015 paper, but relative nonlinearity in competition goes from bad to worse for an invader when we have more clustering. On the other hand, it reduces the negative effect of demographic stochasticity by making the outcomes of the lotteries more predictable. So that's what you get from decompose and compare. Instead of just being able to say that clustering is bad for coexistence, we can decompose the effects of clustering into what they do to storage effect, to relative nonlinearity, and to these new terms that we have as a result of demographic stochasticity. Okay, I've talked as much as I'm going to talk straight from beginning to end. No, I haven't. I'm going to end with one more little bit of sermonizing. I'm going to say, clearly we need more theory. And I'd love to see more empirical applications of ideas like this. We always learn the most when we try to analyze models that are based on real data, because the real world throws you curveballs. When we write down a model, we write down a model that matches our ideas about how things work. We as a group have learned an enormous amount by analyzing models that were driven by data, and they don't act the way we expect. Okay, so thank you very much for your attention, and the four of us will be happy to try and answer any questions that you might have.
Thank you so much, Steve. So if there are questions, then please raise your hand in the participant list, just with the raise hand function, and I will call on you. Any questions? Yes, Sebastian.
Okay, I don't know if this is very relevant or not, but there was work that has been done in interacting particle systems where it's not a finite lattice, but an infinite lattice. I think in the 90s by Claudia Neuhauser and Rick Durrett. Admittedly, they weren't looking at storage effects. I'm not sure how one can compare, but are you aware of that work? And do you know if there are any insights or that one might get from using that approach in this context? In other words, where they write down a hydrodynamic limit and get a PDE, which in this case will be a time varying PDE, where there would be a well-defined invasion growth rate.
Yeah, I mean, we've tried to look at what's out there, including that literature and stuff that Rick Durrett and others have done since then. So the hydrodynamic limit does preserve some clustering, but all of those things lead to equations where you get the expanding disk. Okay, so basically there's something about the assumptions that they're making and that other people are making that leads to expanding disk behavior, and that's not what we're seeing. Okay, I'm not sure what it is, but if we were trying to compute the expansion rate of an expanding disk, there would be theory out there that would help us do it, but that's not what we're seeing. Okay, and I think what's going on, and part of why lots of people see nucleation and we don't, is that a lot of the models assume strictly nearest neighbor expansion. That when you have an offspring, it has to go into one of your neighboring sites. And we allow dispersal that hops over your neighbors and lands a new offspring somewhere else. And that seems to completely change the behavior. Okay, it's sort of like small world networks. You add a small number of long distance connections and suddenly everything is different. Okay.
Yeah.
Sebastian, you have something to say following up on that?
No, that was perfect. Thank you so much.
Okay, yeah.
Yuri, there's Bob and Nadav have their hands up.
Nadav, do you want to go first?
Whatever. I think that you have raised your hand first. So.
Oh, okay, well, that's fine. Yeah, Steve and Robin and Peter and Giles, that was fantastic. Really, really interesting. I have a thought. You mentioned, Steve, at the end that the importance of tying it to empirical systems. And of course, if you think about most empirical systems like the desert annuals to which the temporal storage effect is applied, there's a lot of local spatial heterogeneity as well. And Peter talks about the spatial storage effect. And I think if you added limited dispersal and therefore clustering and with spatial heterogeneity, you're going to facilitate coexistence, all else being equal. So that just be something that people should think about, particularly if they're going to be applying these ideas to empirical systems.
Yes, if you add that heterogeneity, you're going to add spatial storage effect. Yeah. But a key thing that you're going to add, I think, is environment growth, is density growth covariance. Okay. My feeling is that with spatial heterogeneity, and some of Monica Gaber's students here have worked on this, so there'll be some empirical stuff on this coming out. That spatial storage effect has gotten a lot of attention, but density growth covariance, that is, that species accumulate most in places that are best for them, is probably a much stronger mechanism in most cases. And so adding heterogeneity, I think, is going to change things a lot, because you're going to have species clustering, not just because of local dispersal, but they're going to wind up clustering in places that are good for them, right? Where they have high fecundity. So yeah, so we have more work to do. We have to do a 4-way partitioning or a 5-way partitioning, because we have spatial. Thanks a lot, Bob. Thanks. Yeah, it's always good to have more things to do.
As older professors, we know one of the valuable things about being a professor, you're constantly suggesting work for other people to do. So
yes, that's right. And constantly being frustrated when they don't think that it's the most important thing on earth for them to be doing. Yeah. Okay, Nadav.
Okay, just a little question about what I didn't get is the nucleation story. So at least in my mind, nucleation has to do with positive feedback. When you have a population that tends to shrink, but when the population gets larger, it has some sort of positive feedback, alley effect, and then it grows, then small nuclei shrink while large nuclei expand. Right. So what kind of positive feedback do you have in a system which is in a lottery system, such that you should expect for nucleation?
The person who should be answering that question is Jacob Usinowitz, because he studied a lottery model that's very much like ours, only it only had nearest neighbor spread. That's his 2015 paper.
Right.
Okay, so only nearest, right? If you had individual spread larvae only to neighboring sites, you can't move by 2 in one time step. Other than that, I think it was exactly the same as our model, and he saw nucleation. He very clearly saw nucleation in his simulations. So again, it's that when the cluster is small, you're mostly seeing resident species as your competitors.
Yes.
Okay, and when the cluster is large, you're seeing a larger fraction of invaders, and somehow that results in positive feedback. Again, we haven't looked into this because we simply don't see it at all in our simulations.
Nice.
But by some means, in a model that's nearly identical to ours, you actually see this predictable nucleation effect going on, and he has analytic theory that lines up very nicely with simulations, predicting exactly what is the critical size at which expected cluster changes from shrinking to expansion. Okay. I don't know. I just know that it's real, and you don't have to change the model very much in order for that to actually happen.
I see. Okay, thanks.
Yeah.
Thank you. Any other questions? While people are thinking, maybe I have a question. This question sadly will reveal that I'm not completely certain about the current state of the art about how to do this. But one thing that I have always thought about is this combination of spatio-temporal variation, right? Spatio-temporal storage effects and things like that, which is not at all obvious how to do, at least in the classical Chesson style theory. Now, I'm wondering if your numerical method automatically takes care of this, or in other words, just to give you even more tasks to do, what would happen if there was some sort of environmental forcing put on top of all of this?
Environment, some sort of spatial, okay, spatio-temporal variation in the environment, not
Yes.
just spatial, fixed spatial heterogeneity and temporal variation.
Correct.
Yeah, this is a question for Robin, who's worked on that.
Yeah, you can do that in the classical theory. And I have papers from probably around 2005, 2006 on how to do that. I don't see any reason why you couldn't do it with the Efenova approach. But I think first we need to get strictly spatial variation taken into account, and then, 6 months from now we could move on to spatio-temporal.
Okay. Thanks. Excellent. Any other questions?
Can I make a question?
Sure.
Hi, my name is Oscar. So I have a question about your simulations. And you're talking a lot about the role of environmental variation, but I was wondering to what extent you also write the spatial extent of your analysis. Whether the question would be whether you were considering small areas versus large areas. Because I can see, and I don't know the answer, but I can see the situation in which you have large areas, and because of that, you might have more chances for a species to experience different competitive environments. And therefore, because of that, the species can persist in the long run, thanks to having, from time to time, those environments that allow them to have, in the long term, positive population growth rates.
Okay, so you're right. So in a multi-species context, in a big enough lattice, there will be places in the lattice, or in a big enough habitat, let's say, there will be places that are different because you've got different species present or different abundances. So you sort of have spatial, non-stationarity of the environment. Yeah. Yeah, that's an interesting possibility. The stuff we've done is just 2 species, and that keeps that from happening. So we haven't had to deal with it. We have looked at what happens if you make the lattice larger, and just to make sure that 60 by 60, which is fairly easy to simulate, isn't biasing things because you don't have any space for the species to expand into. But the possibility of auto-generated spatial heterogeneity is another possibility. I think you're right, in multi-species situations. Is that getting at what you were talking about?
Yeah. I think it's more or less what you the kind of question the kind of answer I was expecting. But I think it's something that in general we play. Well, in general terms, we play a lot the ideas about environmental heterogeneity, whether we don't consider so much the spatial extent, especially if you are in a rare invader, which start for a very small area. And perhaps not all the area that you can actually benefit from is large enough.
Right.
Yeah. Thanks, Steve.
Yeah.
Thank you very much. Any other questions?
All right, then. Thank you very much for coming and for listening to the talk and for your stimulating questions. Clearly, we have a lot more to do. And as I said, I'll be very gratified if we've convinced some of you to tackle some of these questions yourself, because there is a lot more unknown than there is known. We have our hands full for many years, and many hands would make lighter work. Thank you very much.
Thank you so much, Steve. And thank you everyone for joining us. The next talk in the series, I believe, Geza, correct me, but it's February 9th and it's Tomaka Fell.
Yes.
Yes. Correct. So
niche theory of positive interactions.
Yeah, so niche theory of positive interactions. We're continuing February 9th, same time, Tuesday, right? February 9th, Tuesday, 6 o'clock Central European time, 9 o'clock Pacific time. So thank you again very much for your attention. And thank you so much, Steve. Have a nice rest of your day and see you there and then. Goodbye.
Thank you.
Bye, everyone.
Thanks, everyone.
Bye-bye.
Bye.